And I think everything should be fine now. Let's see what's going on. Okay. So today we'll talk about, we'll start with Markov random fields. We'll continue what you did last time with Trajan. Do you still remember what you did then?
We talked about Bayes networks.
Bayesian networks. Okay. Which were what?
A graphical model for representing data about
a specific problem, right? So it was a graphical model. So a modeling of a problem using a graph. What kind of graph? Directed or undirected?
directed.
Okay, so it was a graph modeling using directed graphs. And what were the issues that you had in those graphs, in that graph, in fact? What did you want to achieve by modeling the graph? Do you know what were the main tasks, let's say? There were two things that you did in that graph. Can you tell me which were those two?
You mean what we use the graph for, or?
Yes. What have you done in that graph? What were the main tasks? What was the graph used for?
Computing the joint probability distribution and marginal probabilities.
Exactly. So you model the problem using that graph for two main tasks. The first one was to compute the probability of the graph of the I don't know, of the model P of X, where by X I mean all the variables associated with all the nodes in the graph. And then this was one of the tasks, and the other one was to identify some marginals, which was somehow derived from the first task. And there is another important task. So these two were somehow related. Compute the probability of the model P of X, and compute some joint probabilities within the model. So if I'm only interested in the probability of two nodes or three nodes or so on, I can compute the marginal probability of those of the variables representing those nodes. But this is one task. Another task was related to, do you know?
Independence between.
Independence, exactly. To find what conditional independence properties hold in the graph. So these are the two main tasks that graphical models are used for: to compute the probability of the model, P of X, and to identify which variable are independent in that graphical model. And the fact that you use DAGs was very nice for deriving the probability of X, because you had the rule that the probability of X is the product of the probabilities of children conditioned on parents, right? Remember that? Does it ring a bell? So every time you had a link between the nodes, a directed link between the nodes, the children was the probability of the children was computed depending on the parent that conditioned that node. And therefore, the probability of the whole graph can be expressed in terms of the product of these probabilities for each node from the graph. So it was easy to derive the probability of X or the marginal probability of some nodes in the graph, because you simply took the product of the probability of each of those nodes from the joint probability that you needed. And it was, so this was for the first task for that deriving the probability of X. And it was a little trickier for identifying the conditional independencies from the graph, because you had to apply deseparation. Do you still remember what deseparation was? Yes or no? So deseparation was a graphical test in which we identified what kind of links connects two nodes, if they are head-to-head, head-to-tail, or tail-to-tail. And based on this kind of nodes, we had something that was called deseparation, which told us whether the paths connecting those nodes or sets of nodes were blocked or not. But the definition of blocked was different in case of head-to-head nodes compared to the other two situations, head-to-tail or tail-to-tail nodes. And this was due to the fact that in graphical in DAGs, we have this asymmetry between the source and the destination of a link, because they are treated differently. And because of this difference between the source and the destination, we had this distinction between the V structure or head-to-head nodes and the other two structures that define the blocking condition. And by blocking condition, we understand whether two nodes or set of nodes are independent or not. Okay, so blocking was related to independence. Now, because of this definition that was different in case of head-to-head nodes, we are trying to search for a different alternative of representing the problem, so a different kind of model, also based on graphs, that would somehow ease the identification of conditional independence. So in DAGs, there was easy to compute P of X, but it was trickier to identify conditional independence. And therefore, we're searching for a different kind of models in which to be easier to identify the conditional independence of nodes or set of nodes, of course. And therefore, if this issue appeared as a consequence of differences between source and target nodes, we are looking into models which don't make a difference between the target and the source of a link, of a connection. And to do that, it means that what we actually are searching for, it's a model that will use undirected graphs. Because if we have undirected graphs, then the source and the target of a link have the same interpretation. They are connected. Basically, the connection can be seen from one node to the other or reversed, because it's similar to having a double directed link, one in one direction and the other in the opposite direction. And therefore, in this way, we eliminate these differences that may arise between the source and the target. So what we're doing here is defining an alternative graphical semantics for probability distributions, such that condition independence to be determined simpler than by using the separation index. And the model that is based on undirected graph is called Markov random fields or Markov network. And this is what we will be talking about today. Okay, so that's what we will start with, and we'll see where this leads. So if we are interested in conditional independence, then we have just like in DAGs, we consider two sets of nodes, three sets of nodes, A, B, and C, and if all the paths from one set of nodes A to a different set of nodes B goes through the set of nodes from C, we say that all the paths from A to B are blocked given the nodes in C. Okay, so it's somehow similar to what you did in DAGs, only that this time we don't have directions on links. Okay, so two nodes are independent, conditioned on the nodes from their path. And starting from this observation, we can go on and identify what is the Markov blanket of a node. Can somebody tell me what is a Markov blanket of a node? You talked with Traian last time. In fact, Traian presented you last time what is the Markov blanket of a specific node from the graph. Can you tell me?
The minimum number of nodes that needs to be observed in order for one node to be independent of any other node.
Yes, but we're not interested in the number of nodes, but in the set of nodes. So is
the minimum set. That's why
the minimum set of nodes. Yeah. The minimum set of nodes that if those nodes are observed, then it means that the node is separated or independent on the rest of the graph. And as we have this definition from the left, it means that for a node to be independent on all the other nodes, it is sufficient to know all its neighbors. For example, if we know this node and this node and the nodes from C, it means that this particular node is independent on all the graph, okay? Because any path that goes from this node, let's say alpha, to anywhere else in the graph has to go through either through the nodes from C or through the nodes that I colored in this representation. So now it's much easier to identify the Markov blanket of a node in undirected graphs because we don't have the situation with the V structure. So now we know that all the paths from the node to the rest of the graph are blocked by the neighbors of the node. So the node is independent of the rest of the graph if the neighbors are given. So this is actually the Markov blanket of a given node from the graph. Do you have any questions here? Okay. Good. So with this representation, it's actually very simple to identify the conditional independence of two nodes, because if they are connected by a direct link, it means that they are not independent. But otherwise, if they are not connected by a direct link, it means that they are independent given the nodes from the path between the two nodes. So independence is easy to identify. But the problem now is, okay, we had two issues. One of them was independence, but the other one was to define a mathematical way of computing the probability of this distribution from that model. So how can we derive P of X? In DAGs, there was a simple way of doing that because we followed the links and we had the probability. So we had the product of the probabilities of the nodes X given parents of node X. Okay, so this was defined. I don't know. The probability was defined like this. Now, we need to derive something similar for undirected graphs. But now we don't have parents because the graph is undirected. However, we have this information that is derived from the Markov blanket that says that if two nodes that are not connected by a direct link, it means that they are conditionally independent given all the rest of the nodes from the graph. So it means that P of xi and xj given all the other nodes factorize this in P of xi given all the other nodes multiplied by P of xj given all the other nodes. This translates in the fact that when we try to define the probability distribution of the graph, of the model, it means that if two nodes are connected by a link, it means that they should be in the same factor. But if two nodes are not connected by a link, by a direct link, it means that they should be in different factors because they are independent if the other nodes are given. So basically, xi and xj don't appear in the same factor in order for the conditional independence to hold if xi and xj are not connected by links. So it means that each element, each factor that is found in the definition of P of x, so the probability distribution of the model, is defined based on all the nodes that are connected through links, through direct links. So if all the nodes are connected by direct links, it means that we have a full subgraph. So we have a graph in which we have a link between all those nodes. And if this is what we are trying to identify, this is called clique. Okay. And therefore, the problem of deriving this probability distribution of X is reduced to finding the cliques, all the cliques from a graph. Because once we know all the cliques from the graph, we can derive a specific factor P for that clique, and therefore P of X will be defined as the product of the probabilities for each such clique. Okay, so if we have the blue clique and the green clique, and we will also have a red clique like this, we can define a probability for each of those. And then P of X will be simply P1 multiplied by P2 multiplied by P3. Okay? Now, we reduce the problem of building the probability distribution of the model to the problem of identifying the maximal cliques from the graph. Do you know what is the complexity of finding the cliques in the graph from algorithm design? What kind of problem is identifying the cliques from the graph? Do you know? Any idea? Is it polynomial? Is it NP complete? Is it, I don't know, exponential? What kind of problem is identifying the maximal cliques from the graph? Any ideas? Philip?
complete.
Exactly. So we identify so we reduce the problem of determining P of X to determining the maximal clicks from the graph. But however, this is an NP complete problem. So we need to somehow simplify this because otherwise we won't be able to fix it. But we'll talk about how to simplify it a bit later. Now, let's suppose that we have these clicks and we can attach a function pc of xc that is greater or equal to 0 and which is called the potential over maximal click c. This is where the c from here comes. And therefore, the probability p of x will be simply 1 over z. Z is a normalization coefficient. Product over all the clicks C out of the potential of each maximal click, pc of xc. Z will be simply the summation over all the x's out of this value. Okay, so it's simply a normalization factor. Now, unlike for DAGs, these potential don't have specific probabilistic interpretation. Okay, so we know that we have a click, and therefore, based on each click, we have to derive a measure that will characterize that click. And this measure is called the potential of the maximal click. Doesn't have a specific probabilistic interpretation, which gives us greater flexibility in how to choose them, but also give us, it helps us because we are able to define the way of computing those potential, but it's also a problem because we don't know how to choose between different alternatives, and moreover, why to make that choice. Now, as I told you, Z is called the partition function, is the normalization coefficient. And if we have m nodes in the graph, each having k states, it means that we have m multiplied by k state variables, which means that in this Z, we should have k to the m terms, which is difficult to compute. And now, since we have this product in the definition of P of X, in order to compute less when we have to derive the parameters and stuff, it's convenient to express this potential as being an exponential. You know, the derivation of an exponential is easy to compute. When we have to multiply different exponentials, it's again easy to compute because all we have to do is to add up the coefficients and so on. So we have a lot of advantages if we define this potential as being some exponential functions. And the potentials are usually expressed as an exponential of minus energy of xc. E of xc is called the energy function, while exponential of minus e of xc, it's called the Boltzmann distribution. Now, when computing the joint distribution, is simply the product of potentials, which means that well, all we have to do is to add up these exponents, and therefore the energy of the system, the total energy at ET, let's say, will be simply the summation over the energies of the clicks, of the maximal clicks. So basically, to compute P of X, it's extremely easy because if we defined the potential as being exponential of some values, all we have to do is sum up those values, and we have the total energy and therefore all we have to do is to compute the value e to minus total energy. Okay. And now let's see how one model would be would be useful, or how can we use this modeling of a problem, and then we'll see how we can identify parameters and so on to make it efficient. Because as I told you, there are exponential number of terms, and it is difficult to compute it like that, and we need to do some tricks in order to reduce the complexity, so that we can have efficient algorithms for computing probability of this probability distribution of the model. So let's think of a problem. We have this original image, which contain some pixels that are either -1 or +1, and basically this is the target. This is what we would like to obtain when we are given this image, and this image is a noisy image that is obtained from the original picture, so from this picture, by randomly flipping the sign of pixels with small probability. So in here, in the noisy image, we will have the pixels having -1 or +1 values, and the pixels are obtained from the original picture that we would like to reconstruct, that has some pixels that are randomly flipped. Okay. However, as you can visually see, there is a high correlation between the picture from the right and the picture from the left. So there is this flipping of pixel is for only a few such pixels, and basically, given the noisy picture, what we want to do is to reconstruct the original picture. Can you tell me, so we would like to build a model that is trying to model this problem. So we would like to have a graph-based modeling that uses an undirected graph to model this problem. This is what we have. This is what we need to compute. How can we model this problem using an undirected graph? Let's see. Any idea?
We represent each pixel by a node. And
okay, each pixel from which picture?
From the noisy picture, we don't have access to the denoised one, right? The original.
Right. We don't have access to the denoised one. So for the right picture, we represent each pixel as a node. Okay.
And we want to compute for each pixel the probability of it having been flipped. I think.
So one second. So first we have the nodes from the noisy picture. I'm interested in the links. What will the links be like?
Every pixel it's linked with its neighboring pixels, I'd say. I don't know.
Okay, it is true. How many links?
8 or 4. I don't know.
at most 4, let's say.
Okay.
Up, down, left, right. Okay. So each pixel has at most 4 links that are represented by its neighbors, and these links should have a high connection because most of the time consecutive pixels or pixels that are next to each other should have the same color. Okay, so they should have a high correlation. But now these are the scene values, okay? Because we know what is the sign of each such pixel. So this is what we know. Now we have to connect what we know to what we would like to get. So for each pixel from here, we need somehow to find the connection of the, well, I didn't draw the correct line, but we need to see how to connect each such pixel from right to its corresponding pixel from left, and to get the correct value of those of that pixel. Okay, so what we described till now, it's only one part of the problem, the one that describes the picture that we have, the picture that is seen or given, and we also need to connect to what we need, what we have to compute. So basically, we have the connections that you said already, but we still have to find the color of the nodes from the other picture, from the left picture. So now we're constructing a similar graph for this picture, but we are connecting each pixel from here to the corresponding pixels from the noisy picture that we have, and we'll get to a structures that is like this. So we are seeing the values of y's. So this is the picture from the top is the one that is given. We see it, and the nodes from below, so these nodes are corresponding to the initial picture, and basically it's what we need to compute, and they are hidden. We don't know their values, and we need to compute them. But we know some things. We know that they are connected one to each other because neighboring pixels should have the same color, and they are connected to the corresponding pixel from the noisy image that is seen. So we know its color. And therefore, this is the Markov random field model associated to the problem. We have two types of clicks. Or let's look at the picture. How big are the clicks that we can construct in here? How large? What is the maximum dimension of the clicks?
2 nodes?
2 nodes, okay? So either we have connections like this, where we combine the seen pixel with the hidden one, which we don't know and we want to compute, and this is one kind of click, or we have this kind of click where we connect 2 additional pixels from the image that we need to correct, let's say, and we don't know their values, but we know that they are strongly correlated, and they should have most of the time the same color. And now we have these two kinds of clicks, each of them representing some types of energies or correlations. We have the connection or click between xi and yi, the vertical click, which is defined by minus eta xi yi, and expresses the energy that represents the correlation between the two pictures. And the other type of clique is between xi and xj, and has the value minus beta xi and xj, and is the energy expressing correlation between neighboring pixels. First, eta and beta are some factors that we need to identify. And this minus is here because, you know, what's happening is that we want low energy, because what we will try to do in this system is to minimize the energy of the system. And therefore, we would like to have low energy when the terms xi and yi, or xi and xj, have the same color, or have the same sign. So basically, we will define the error as being a situation where the two elements after the parameter have different sign. So let's say -1 and 1, the product will be negative. If we have 1 and -1, again, the product will be negative. And with this minus from the front, minus with minus will become plus. And therefore, if we have an error, the energy will go up. If both elements xi and xj, or xi and yi, have the same sign, then the product will be negative and the energy will go down. And therefore, we start with a given energy, and then we will try to make consecutive steps in minimizing this energy. When we get to the minimum value, we say, okay, this is the result that we wanted. Make sense? And now the definition of the energy of the model, so of the whole system, energy of joint original or noisy picture, and the one that we would like to reconstruct, it will be another parameter h multiplied by xi, which is a bias for the pixels in the noise-free image, because we still want to obtain an image that is similar to the one that we have to denoise. Okay, we don't want to have a noisy picture of a dog and to obtain a cat. And this is why we need to put some bias on the original pixel, so that we get the same elements in the denoised picture. So therefore, we have these elements that will give some bias for the pixels in the noise-free image. Minus beta xi xj, which is the energy between the two pictures. Minus eta, the energy between neighboring pixels, and minus eta xi yi, which is the energy between the two pictures. And now the joint distribution between xi and xj, p of xi and xj, is simply 1 over z. This is the partition function, exponential of minus the energy that we just defined here. And this is the model that we would like to have. And since this all we would like to have is increasing the probability of the model, so p of x and y, which means that we would like to decrease this energy. Do you have questions? Okay. So we will start from the noisy image, and this is what we get in the end, a restored image using ICM, iterated conditional modes. Basically, we have y, and what we want to do is to find the x, so that p of x given y, so this is y, this is x, and we want to find the x that will maximize the probability p of x given y. This is what is called an Ising model. I think you heard of Ising models. Have you? for example, in games, sometimes you have the option of choosing anti-aliasing, which is an icing model. Also in cameras, when you set up the parameters of the camera, you also have an anti-aliasing parameter that you may turn on or off. And basically, this is what that icing model is doing. So this ICM model that is used says like this: first, init xi with yi. So I'm initializing the picture that I want to obtain to the values of pixels from the original or from the noisy picture that we get, and then for each node xj, we set it both to both values, -1 or +1. So for each pixel from here, we say, okay, let's see what's happening if the picture would be -1. Let's see what the result is when the picture is +1. Evaluate the energy in each case, and then set xj to the value that will give me a lower energy. Once I did this, we continue with the next pixel and so on until a stopping criterion is satisfied. Okay, so I'm taking some pixels, then I'm verifying them, get another batch of pixels, I'm verifying them, and so on. But I need to have a policy that ensures that all the pixels are investigated before investigating again the same pixel. And I do this a couple of times, so I go through a couple of cycles in which I evaluate the system until the energy doesn't decrease anymore, or the decrease is too low compared to what I'm investing in doing another cycle. Can you tell me what kind of algorithm is this one, ICM? Again, from algorithm design perspective. Is it backtracking? Is it divide impera? I don't know, dynamic programming, greedy? What kind of algorithm it is? Anyone?
Well, since we check every node independently, and we don't build like a possible assignment of values to each pixel, it's not backtracking.
It's not backtracking, it's true.
So I'd say it's greedy because we choose the best.
Exactly, it's greedy. And the problem of greedy is that we may end up in some local maxima. In this case, local minima. So instead of obtaining the global minima, this ICM model might end up in local minima. So this is the result that can be obtained with ICM and has around 96% accuracy. But starting from the same picture using a different algorithm that is called graph cuts, we may get up to 99% accuracy. Because again, it's a greedy problem. It's fast, which is nice, but it's not guaranteed to end up in the global minima. So we might end up in local minima, which means that we might not get the best out of the original picture. Okay, makes sense? Now, we found a way of defining probabilities probability distribution in undirected graphs, but we saw that this way of defining the probability requires the fact of identifying clicks. And Philip told us that it is an NP-complete problem. So what we can do is to try to start from simpler problems to see how we can scale up. And similar to what you did with Traian, we'll start first with chains, and we'll see how we can convert them and what's going on there. And then we'll try to increase complexity as we go to more complex models. So first of all, how can we transfer the knowledge from a DAG chain to an undirected chain? So if we had the DAG, we had something like this. So we have x1 that goes to x2 and so on until we get to xn. And the probability of the probability distribution of this chain, it will be p of x1 multiplied by p of x2 depending on x1, because we have this direct link between x1 and x2. X3 probability of x3 depending on x2 and so on, until the end where probability of xn depends on xn minus 1. The corresponding model will be something like this, where we have this chain. Again, what is the maximum value of a click in this chain? How many nodes, or yes, how many nodes has the maximum click from this chain?
Still 2 nodes.
Still 2 nodes. And how many clicks do we have in the graph in this chain? So
n minus 1.
N minus 1. Okay. So this will be the first click. This will be the last click, and it will be n minus 1 such clicks. And therefore we can define this probability p of x as 1 over z, the partition or normalization factor, multiplied by the potential of the first click, multiplied by the potential of the second click, and so on, multiplied by the potential of the last click. And now we can try to make a mapping between the values that were found in the probability of x in the case of DAGs and what we have in here. And this is easy to make because we have almost the same factors. We have the click between the first node and the second node, and in here we have probability of x2 given x1, but we will also have to take this p of x1, which is the initial probability of the first node. Then we have the potential of the second click that depends on x2 and x3, and the next term from DAG, from the DAG definition, is the probability of x3 given x2. Finally, we have the potential of the last click that is similar to probability of xn given xn minus 1. So there is a high equivalence in between chains in DAGs and chains in undirected graphs. You can see that it's easy to represent the potentials as the probabilities of the child given the parent, except for the first click, where we also have to incorporate p of x1, probability of the initial node. But the rest, and also to compute the partition function and to divide the probability by this value. But anyway, the correspondence is easy to make and easy to understand. Now, there are some issues. So when we have directed graphs, we can have situation like this, where we have dependency of a node based on multiple other nodes. But if we want to translate this graph into an undirected representation, it means that we should have direct connections between x1 and x2, x1 and x4, x2 and x4, x3 and x4. So x1, x2, x3, and x4 should be in the same click. But that means that we should also add some values, some links from here, which are not in the initial undirected graph. So basically, what we'll need to do is to add additional links between all pairs of parents of node x4, which is called moralization. And after moralization, we get a moral graph that looks like this. Because since we need that all the nodes to be in the same factor, because in here we will define for this the definition p of x is p of x1, p of x2, p of x3 multiplied by p of x4 depending on all the other nodes. So in here x4 is not independent on x1 or x2 or x3, and therefore if x4 is not independent on them, it means that it should be placed in the same click with x1, x2, and x4. And therefore, we need to add these extra links from here. Now, if we have this, we can define this moral graph by having a potential depending on x1, x2, x3, and x4, okay, on all the variables. But we can also think of this graph as having some facets. So we can think of this as being a click. It's not maximal, but it's a click. And then this is another click. And then this is another click. And we also have a click formed by x1, x3, and x4. And therefore, we could define this click as being the product of the partition function multiplied by the click phi depending on x1, x2, and x3, the one from top, multiplied by the click formed by x2, x3, and the x4, the one from the right, multiplied by the potential of the click x1, x2, and x4, the one from the left, multiplied by the click of x1, x3, and x4 that I couldn't, it is the one from here. Okay, and now again we can try to make some corresponding elements between this definition from DAG and the new definition from undirected graph. However, it should be noted that they don't represent the same independence as it is in the original graph, because we had to add extra links between x1, x2, and x3. So basically, by moralization, we discarded some conditional independence from DAGs, and the two graphs can express different conditional independence property. If we consider the set of all the probabilities from the world, only some part of them can be represented by DAGs, the one with green. Others can be represented by undirected graphs, and there is a high part of these probabilities that can be represented by graphical models that can be perfectly represented by both directed and undirected graphs. Now, if we have something like this, we cannot represent it exactly as an undirected graph because we will need to do moralization, okay, because we have to add this link. But in the original graph, we have A independent of B given nothing. If we remember, this is a V structure, and therefore they are independent if we don't know anything. But however, if we know the value of C, they become connected. Okay, so they are independent if nothing is known, but if C is known, they are not independent anymore. So this cannot be represented perfectly as an undirected graph. We have to add moralization, as I told you. On the other hand, if we have something like this, we cannot represent this graph exactly as a DAG, because in here, if we don't have anything, it means that A is not independent on B. But however, if these nodes are given, then A and B become independent. Also, C and D are independent if A and B are given. And this undirected graph cannot be represented by a direct graph, by a DAG. Now, we'll see in a moment how we can represent them using a unified representation that can be used for all kinds of graphs. But first, let's talk about a bit about the inference in graph models. I think Traian also told you something last time. If we have a model like in the left part of the picture here, the joint probability P of x given P of x and y, the joint probability, can be defined as being P of x multiplied by P of y given x. However, if we have something similar to the problem with the two pictures that we talked earlier, we might have y observed, and then what we are interested in is to find the x that maximizes the observation of y. So in this situation, we may consider P of x to be a prior distribution over x, and try to determine the posterior P of x given y that maximizes the observation of y. And in this situation, what we can do is to use summation and Bayes rules. And actually, the inference will change from the one direction to the other direction. Okay, because if we know that P of y is the summation of P of y given x multiplied by P of x, it means that we can write this as being P of x and y divided by P of x, which translates into P of y given x multiplied by P of x divided by P of y. And this we have from here, and also y is observed. And now we can compute P of x given y using Bayes rules. Now, this was inference in DAGs. Let's see how we can do inference on a chain. So we've seen earlier that we can, if we have a chain like this, then the probability distribution of the chain is defined like 1 over z, and then the potential of each click from the chain. What's happening? We have n variables, each having k states. It means that each such click will have a k-square table to define all the parameters of this click. Does it make sense? So if x1 has k states, x2 has k states, it means that we will have a table with the states of x1 on one side, the states of x2 on the other side. We have k values in here, k values in here. So this will be a k-square table. So we'll have to identify k-square values. If we have n-1 such clicks, it means that in total, this chain will have n-1 multiplied by k squares parameters. Now, if I want to evaluate the marginal probability of value xn, all I have to do is to summarize or marginalize over all the other variables except for xn, which means summation over x1 of summation over x2 of summation over xn minus 1 multiplied by summation of xn plus 1, finally up to xn big N, capitalized N, out of P of x. And therefore, if we compute first P of x and then we make all the marginalizations or the summations, again, we will end up in k to the n values. So again, it's difficult to compute, it's difficult to find enough data for this, and therefore we will try to see a way to determine this P of xn with a number of parameters that is similar to what we have in here in computing the number of parameters from the chain. And to do this, we need to observe something. Let's look at this element. This element is the only element that depends on xn. Nowhere else in the chain we'll have these xn values. So if we first apply the marginalization over xn, all these elements up to here will be independent of xn. So we can, if we write P of x as in here, and we have to marginalize over xn, we can consider this to be constant from the point of view of xn, and to put in the summation only this part, because this one is the only that depends on xn. On the other end of the chain, this term is the only one that depends on x1. So we can break this chain somewhere in the middle, where we have xn that we need to compute the marginal probability for, and try to do summation over x1 for the first click, and then out of this summation we remain only with x2, that if we summate over the next click, so we make summation over x2, then again we will obtain a term that depends only on x3, and so on. Each such summation will basically remove one term from the chain, and it's in this way it's much easier to compute, because if each summation will eliminate one such node, this summation will only involve k squared terms, because it's we are making summation over only this term, which has only k squared terms. So if each summation will remove such nodes from the graph, it means that all we have to do is to make n-1 times k squared operations, and we will be computing efficiently P of xn. Does it make sense? Are you with me? Can you still hear me?
Yes.
And does it make sense what I'm saying?
Yes.
Great. Let's continue then. So now we'll try to define exactly what I told you. So P of xn will be seen in terms of what's happening up to here from both ends. So one end will start from x1 and do summation on each click up to xn. The other one will start at the end and do summation over the clicks in the reversed order from the end to the point where I would like to compute the marginal probability. And therefore we will have 1 over z, the normalization factor, summation over xn minus 1 out of potential of n-1 to n, so of the last two nodes, multiplied by summation of the previous two and then previous two and so on, and this is up to summation over x1 over the first two elements. Again, this has k-square elements and will lead me to something that depends only on x2. The next one has again k-square elements and leads to a measure that depends only on x3 and so on. And we define this this part as being mu alpha of xn. From the other end, we will have the most imbricated term will be the potential of n-1 to n summation over xn of the final variable out of this potential. And we will get, so we will have k-square parameters, and it will give us an equation in xn minus 1. And then we'll summate over xn minus 1, and we'll have again k-square elements, and will give us something depending on xn minus 2, and so on. If we go back up to here, this will have again k-square elements and will lead us to something that depends only on xn. And now when we have both, and we define mu beta of xn as being the element that reaches xn. And now we have the last term that comes from the left. It will have k-square terms, and it will give us something depending on xn. The term coming from the right, it will have k-square terms, and it will only depend on xn. And now, since we have the probability of xn, we have actually all we need to do, all we need to compute this probability p of xn, as both the terms that reaches xn depend only on this term. Does it make sense? And therefore, well, this is what I told you. Each summation removes a variable from the distribution or eliminates a node from the graph, and therefore the total complexity of this algorithm is k-square, which I need for computing each of these summations multiplied by n-1 is in fact in here, because we have n-1 such cliques that we have to evaluate, but is an O of n multiplied by k-square. Okay, so we can compute, instead of evaluating p of x and then doing all the summations, which lead us to an exponential number of parameters, we have instead n multiplied by k-square operations, and we can compute p of marginal xn. Now, we can do something smarter. We can define these terms recursively. So if we want to define mu alpha of xn, what will be? Well, it will be the summation over xn minus 1 out of the potential of phi n minus 1. So out of this potential, which is multiplied by the summation over the next and the next and so on, and the first. And if I want to define mu alpha of xn depending on mu alpha of xn minus 1, then it's simply this potential of the last clique xn minus 1 to xn multiplied with the value up to here, okay? And the value up to here is simply mu alpha of xn minus 1. So mu alpha of xn can be defined as summation over xn minus 1 of the potential of the last clique, the clique from n minus 1 to n, multiplied by mu alpha of xn minus 1. And we can interpret this in terms of messages sent. We can interpret mu alpha of xn as a message sent forward along the chain from xn minus 1 to xn. In the same way, we can define mu beta of xn as being summation over xn plus 1 out of the potential of the last click before xn. So the click from node n to node n plus 1, multiply with mu beta of xn plus 1. And the interpretation is a message sent backward from the end of the chain to xn. Okay, so basically from xn plus 1 to xn. And now we start with mu alpha of x2 will be simply the summation over the first click, summation over x1 out of the first the potential of the first click, and mu beta of xn minus 1 being the summation over the last variable xn out of the potential of the last click. So since we define this recursively, these are the points where we start from. This is the first message that is sent forward, and this is the first message that is sent backward. Now, each of the messages sent to xn comprises a set of k values, one for each choice of xn. Okay, so in here we'll get a vector that has k values, one for each of the states of xn, and also this one will have the same value k with one element of for each state in which xn can be at the moment. And therefore, if I want to evaluate z, now all we have to do is to make the summation over all the states of xn. So this is k values out of the messages that are sent forward and backward from this from the xn's neighbors to xn. So if I'm multiplying the message sent forward to xn with the message sent backward to xn, and I marginalize over all the values of xn, then we only need O of k operations to compute this value. So to compute all the products from here, so marginalization over all the variable x and xk, let's say, with k different than n, so p of xn equals to mu alpha of xn multiplied by mu beta of xn. So sorry, this is z. To compute these two elements, we need O of n multiplied by k squared. To compute z, we need O of k. So to compute any marginal, since we have these values, we only need O of n multiplied by k squared. If we want to do it for all the variables, for every xi, it means that we add another n, because it's for e from 1 to capitalized n, compute p of xn, compute p of xi in this form. So the whole complexity to compute all the variables or the marginals will be n squared multiplied by k squares. However, if I'm trying to compute the marginal from here, I'm also computing the marginal for here, because when computing mu alpha of xn, I also need mu alpha of xn minus 1. I also need mu alpha of xn minus 2, and so on. So I'm computing these values already. Also, when I want to compute the marginal of xn, I have to compute mu beta of xn, mu beta of xn minus 1, and so on. So I'm also computing some part of this nodes of the messages sent backward and forward up to xn. So it doesn't make sense to compute these values again and again for all the values. For example, if I'm computing only two things, if I'm computing the marginal for xn, it means that I don't have any backward messages, but I have all the forward messages. So if I'm computing P of xn, then I get all the forward messages. If I'm computing P of x1, I don't have forward messages, but I have backward messages. So I'm computing all the mu beta messages. So only with these two, P of x1 and P of xn, I'm actually getting all mu alpha. Sorry, is without. So I'm computing all mu alpha of x size and all mu beta of x size. And now I'm computing z anywhere I want. And now I can compute P of xi anywhere. Okay, so I can compute P of xi anywhere I want. And this will not take me to n squared multiplied by k squared, but it will take me to n multiplied by k squared, because this requires n multiplied by k squared, this requires n multiplied by k squared. So to compute those, it means that we have 2n multiplied by k squares. To compute z, we need O of k, which is lower than this, so this is the complexity that we get. And then, since we have all the terms, we can compute P of xi for any node without having to add any more complexities. So this will leave us to O of n, and therefore the end complexity of the whole process will be O of n multiplied by k squared. So to do inference on the chain, all we have to do is to compute local marginals, which is O of nk, O of n multiplied by k squared. And that means launching a message from x1 and propagate it forward up to xn. So I'm propagating forward from one end to the other. And during this process, I'm computing and saving all the forward messages. Then I'm launching a message backwards from xn to x1, and I'm computing and saving mu beta of xn. Afterwards, at any node, anywhere I want, I'm computing the value of z as being summation over xn out of mu alpha and mu beta of xn that were previously computed. And then for all the variables P of xn, I can compute 1 over z. I have z here, multiplied by mu alpha or multiplied by mu beta, because I already have stored them. And all is okay. Complexity remains of n multiplied by k squared. Moreover, if we have some observed variables, their corresponding variable are simply clamped to their observation instead of summation. So the computation is simplified where we have seen values. And if we want to compute the joint distribution of two neighboring nodes, this value is simply 1 over z, the message received by the first node multiplied by the potential of the click between the first node and the second one, multiplied by the message received backwards by the second node. And this way we can compute any joint distribution that we would like. Do you have any questions before going forward? So this is an important thing. If we have a chain, all we have to do is to pass a message from one end to the other in both directions. In this process, we compute and save all the messages sent forward and backward. And based on this, we can compute the probability, the marginal probability of each node anywhere we want on the chain. We also have the opportunity to compute any joint distribution, any joint probabilities that we would like by seeing what is the components of that join variables. So we compute the product of the click of those variables and the message received forward by one end and the message received backward by the other. So it's easy to compute. Now, we have this issue of having different types of trees. We have undirected trees that we talked up to now. We had DAGs that Traian presented you last time. And we also have what is called polytree, where each node has multiple heads, multiple parents. And we saw that to compute the marginals, if we had chains like this, it is very easy. So what we would like to do next, we would like to get a representation that can fit all these three types of trees, and moreover to use what we've learned from the chain inference from undirected graphs in this new representation. So the representation is called factor graphs, where we add some specific nodes that are called factors, so that the global function of several variables is expressed as a product of factors over subsets of those variables. So we introduce these factors, and we'll have a bipartite graph. Moreover, the factorization P of x, the probability distribution of such a graph, becomes explicit in terms of the factors that we are using. So the probability P of x will be the product of the factors that depend on a subset of variables. In our situation, it will be fa that depends on x1 and x2. So fa of x1 and x2. Fb depends on x1 and x2 as well. Fc depends on x2, x3. And Fd depends only on F3. Moreover, if we want, we can also group the terms that depend on the same variables. For example, Fa can be joined with Ab, and a single parameter can be defined. And also, Fc and Fd can be joined and to have only one parameter there. The nice part of this is that any kind of graph can be represented as a factor graph, and moreover we have multiple ways of doing this. For example, if we have a graph like this, we may add a single factor f that depends on all three nodes and has the same potential as the original potential of the graph, of the undirected graph. We can put additional terms in order to stress more the importance of some specific nodes from the graph. So we can have this time fa depending on all three variables multiplied by fb depending on x2, x3, and this will be the potential of the initial click. Or if we want, we can add factors that depend only on only subsets of variables, and we can have something like in here. And this is what we are doing for undirected graphs. If we have directed graphs, so this is somehow the situation where you saw that we cannot represent exactly the same graph in DAGs and undirected graph. So This is the original graph that couldn't be represented or expressed as an undirected graph. This is the probability that we get for it. And again, we can represent it like this to put a single factor that has the values from here. Or we can add multiple factors, like to stress differently the importance of x1 and x2. So we can say, let's say, for example, fa is p of x1, fb is p of x2. So we have this equivalence from here to here, and then from here to here, and then fc to be only this the dependency part, p of x3 depending on x1 and x2. So we have again multiple ways of representing these factor graphs. And as I told you, what's more important for all types of trees, we can define a polytree. We can define a factor graph that will perfectly represent those trees. So if we have polytrees, we can first transfer them to undirected graphs, but this will lead to cycles due to moralization. And since we would like to use some algorithms that are similar to the chain inference, you saw that those algorithms were defined recursively, and therefore we would like not to have such cycles, because when we have subcycles defining recursively, the terms will lead us to serious problems, and therefore we don't like to have some representation like this. Okay, we don't like this because it has cycles, and we don't like cycles, and therefore we can transform them to polytrees with factor. We can transform them to factor graphs that will preserve the tree structure. So in here we have a tree. If we do moralization, we'll transfer to a cyclic graph, which we don't like. But if we use factor graphs, we can represent it like this, and we preserve the tree structures, which is essential for efficient inference, because we can apply something that is similar to what we did to the chain. And now we will go through two algorithms that are important. The first algorithm is the sum product algorithm, and it's an algorithm that was designed for factor graphs. We first convert the original graph into a factor graph, and this way we can deal with both directed and non-directed models using the same framework. So it's adaptable to both DAGs and undirected graphs. And with the help of this sum product algorithm, what we would like to do is to obtain two objectives, to reach these objectives. First, we would like to have an exact inference algorithm to find marginals that are applied to these factor graphs. This is one thing. And moreover, if we need several such marginals, we would like to be efficient in sharing the computation for them. So we would like to do something similar to what we did in chain, where we didn't want to compute the same things for each node, but to use the information that we already computed for one node to compute the marginals for the other nodes. And it will be a similar framework as what we did in chains. So first we need to find the marginal p of x for a variable node x from here, and we see that x is connected to a set of factor nodes, and those factor nodes are connected to a set of other variables except x via this f of x. So x, a node, is connected to other nodes which are denoted by fs of x and xs. But the connection is done through this node because we have bipartite nodes, graphs, sorry. And if we denote by fs of x and xs, this is the target, this is the source, okay? So we have in this representation, first we put the target and then the source. And if we denote fs of x and xs, this will be the product of all the factors in the group associated with factor fs. So all the factors from this blue area. And if we want to compute p of x, it will be the marginalization over all the terms except x out of p of x. And p of x will be defined as being the product over all the neighbors of x, so the product of the elements that come from each link that x has. So the product of all these values that again represent the product of all the factors associated with a given factor node fs. Okay. Now, what we would like to do is to have this term placed in here, but we would have to do with summation over the product, and we'll do something like what we did in the chain. We'll interchange the product with summation so that each summation to remove some parts of the graph. And this way we will obtain an efficient algorithm. So we'll consider again a message passing algorithm. So p of x is the product of s being part of the neighbors of x out of this information that comes from the blue cloud. We'll denote this information as being the message sent by the fs to x. Sorry. So is the message sent from fs to x? Okay, so it's this message, and this message. So we make this notation is the summation over all the other nodes associated with fs out of fs of x and xs. So the interpretation of this is a message from the factor node fs to the variable node x. Evaluate these messages fs of x and xs. It means that what we will have the message. Now you know in the previous slide the cloud was something like this. Now this was this was the area that we needed to infer the value of mu fs to x. Now to evaluate this, it means that we will have the value of the factor node multiplied by what's coming from these smaller areas. Okay, we have one there and we have another one here. And again, we will try to define something recursively, because this will be in fact the message that is received by these nodes from another factor graph. Okay, and again, we can define this recursively. So the message from fs to x will be in fact the summation over all the variable from here out of fs, the factor node, depending on all these variables plus the variable for which we are computing. Okay, so the message of fs to x, it will be marginalization over all the variables that fs depend on plus the variable x, multiply with the messages that are received by each of such nodes on all the links that they have. So the messages that are received, the messages that are received by the factor graph from all the connections that it has. So the messages that come from the other variables to the factor graph. Okay, so it's a summation. It's in fact marginalization over all the other values that are connected to fs, except the value x for which we compute this message, multiplied with the messages received by the fs from the other connections, from here, and all the other ones that come from these directions. Now, to compute the message that comes from xm to fs, it will be simply the summation over all the variables multiplied by the product of the factors that these nodes are connected to. Okay, and therefore we go again into a recurrent representation, because again we interchange these two and we get that the message from a variable to a node, it will be the product of all the messages received by that node. So if I have a message from a factor node to a variable node, then we make the summation, we make the summation or marginalization over all the variables out of fs multiplied with the messages received by xs. So from x to fs. If we have a message to evaluate a message from the node values to a factor graph, it's simply the product of the messages received from the other factor nodes to the element x. And since we have recursion, we need to start from somewhere. So if the first node it's a variable node, it means that the message sent forward is equal to 1. And if the first node it's a factor node, it means that the first message is f of x. And with these values, let's see how we can compute. So this is an example, and then we'll do the algorithm and we'll continue from there. So the sum product algorithm can be viewed in terms of message sent out by factor nodes to other factor nodes. And in this example, in order to compute the blue arrow, so it will be summation over fs that depends on x1 and x2 multiplied with the message from x1 to so the message to fs from x1 multiplied with the message from x2 to fs. Now, to compute this message, this is a message from a node to a factor graph. So this message will be simply the simply the product of these two messages. The message from x2 to fs will be simply the product of these two messages. So if we multiply these two messages, these two from here, we will get mu of fs from x2. If we multiply these two messages, we will get the message from x1 to fs. And then if we marginalize over x1 and x2, the product of fs of x1, x2 and x3 should be here also, because fs depends on all three variables, multiplied by the message received from x1 and the message received from x2, then we obtain the value of the message sent from fs to x3. Now the algorithm is like this. We have two different kinds of messages, from factor nodes to variable nodes that are defined like this, and from variable nodes to factor nodes that are defined like this. And now, to evaluate a message sent by a factor node to a variable node, first take the product of all the incoming messages along all the other links coming into the factor, multiply by the factor, and then marginalize over all the variables associated with the incoming messages. And a factor can send the message forward to the variables only when it has received incoming messages for all the other neighboring variable nodes. Next, to evaluate the message sent by a variable node to a factor node, all we have to do is to take the product of incoming messages over all the other links, and this variable node can send the message forward to the factor node once it has received incoming messages from all neighboring factor nodes. The marginals that we try to compute is given by the product of the incoming messages along all the links arriving at the node, and each such message is computed recursively until we get the first node. And depending on what type of node it is, if the leaves are variables, then the factor node is 1, and if the leaves are factor nodes, then is f of x. So the algorithm is like this. Pick an arbitrary node as the root. It doesn't matter which node is the root. Compute and propagate messages from the leaves to the root. Then compute and propagate the messages from the root to the leaves. And then compute the product of received messages at each node, for which the marginal is required, and then normalize if necessary. The algorithm is independent on which node was chosen as the root, and complexity is simply twice the complexity for one variable, because all we have to do is send two types of messages. First, from the leaves until they reach the root, and then from the root until they reach the leaves. And let's see an example. So we want to compute let's say probability, the marginal probability of x2. In this situation, p of x, it will be the product of the factor graphs, fa that depends on x1 and x2, fb that depends on x2 and x3, and fc that depends on x2 and x4. And now we're choosing x3 as being the root, and we're sending messages from the leaves to the root. So first we have the message from x1 to fa is 1, from x4 to fc is 1, because are the messages sent from the first node to the factor graph. Then the message from fa to x2, which what value will have? Well, is the product of fa that depends on x1 and x2 with the message that was received by fa, which is 1, okay? And then is marginalization over all the other variables. So fa depend on x1 and x2. I'm computing the message to x2, so it's summation over x1, okay? So mu of the message sent from fa to x2, it will be the product, the summation over x1 over the product fa of x1 and x2, and this message received by fa. Similar, the message from fc to x2, so this message, it will be fc multiplied with 1, multiplied with this message, and summation over x4. Okay, so it's summation over x4 out of fc multiplied with 1 that is taken from here. Now, I have received all the messages to X2. To send the message forward to FB will be the message from X2 to FB. It's a message from the node to a factor, and therefore is the product of all the messages received by X2. So is the product between mu FA to X2 multiplied by mu FC to X2. Finally, the message from FB to X3, it's this marginalization over X2 out of FB multiplied with the message received from F2. So it's marginalization over F2, FB that depends on X2 and X3, multiplied by the message that is received here. And now we ended up the first pass of the graph. Now we're passing the messages in the other direction. So we pass the directions in the opposite direction. First message is 1 because it's the initial message, and then the message from FB to X2 will be the summation over X3 because this one depends on X2 and X3, so it's marginalization over X3 over the FB multiplied with 1, that is this message. Next, the message from X2 to FA. Well, I said that in order to send the message forward, it means that X2 has to receive the messages from all the other connecting factors. So to compute the message from X2 to FA, we need this message, but we also need this message that was computed in the previous step. So the message from X2 to FA will be the product between the message sent from FB to X2 and the message sent from FC to X2. Next, the message sent from this one, from FA to X1, it will be the summation over X2 of the message received by FA, so mu X2 to FA multiplied by this factor FA of X1 and X2. Similar, in order to compute this message, we need this message that is sent from FB to X2, but we also need this message that was sent in the first pass from FA to X2. So the message X2 to FC, this one, is the product of the messages received by X2 from FA and from FB. And now to compute the final message, the message from FC to X4 is the summation over F2 multiplied by FC of X2 X4 and the message received from X2 by FC. Is it clear? Do you have questions? Do you still hear me? We have, I don't know, 5 or 10 more minutes before finishing. I'm sorry for taking a longer time than what it was supposed to, but I would like to finish in order for next time to go to a different topic. So this way is how to compute all the messages. Now, if we want to compute P of XA, P of the marginal of X2, we only need to compute the product of these messages, the messages from FA, FB, and FC to X2. We have those messages computed in the previous slides. So if we're computing this product, all we get is simply the summation over X1, X3, and X4 out of these factors, which in fact is the marginalization over X1, over X3, and X4 out of the probability P of X, as initially we defined P of X as being this product of factors. And if we take the values that we computed earlier, which are defined in here, you can see that we get to the same values. So this is a way of efficiently compute the marginals. Now, the second algorithm that we'll be talking today is an algorithm that is derived from the sum product algorithm, and it has as goals to find x max that maximizes p of x, and also the probability of x max. So to find what is the attribution of different variables so to different states, so that to maximize the probability distribution of x, and also to compute this maximum probability. And as a rule, in general, maximum marginals is different than joint maximum. For example, in here, we have probability of x being 0 is the summation, so it's 0.6. The probability of x being 1 is 0.4. So probability of x is maximized if x equals to 0. For y, probability of y being 0 is 0.7, probability of y being 1 is 0.3. So the y that maximizes p of y is 0. However, the maximum value from this table is here. Hello. Can you still hear me?
Yes, we can hear.
Because the computer froze for some seconds. So the maximum probability is here is 0.4. And we can see that the value of x that maximizes the joint probability p of x and y is the value 1, while the value of x that maximizes p of x is 0. So the argmax of p of y, argmax of y is also 0. So in here, argmax of p of x and the joint probability is 0. Okay, so the maximum probability is found when y equals to 0 and x equals to 1. But you can see that the value of x that maximizing p of x, the individual probability for x, is different than the value of x that maximizes the joint probability. So therefore, we cannot decouple the identification of the individual variables that will maximize their own probabilities. And this is a problem because we need to consider the joint probabilities and to compute the maximum probability with all the variables. And therefore, we go back to maximizing over a chain. So we go instead of instead of sum product, we'll get to max product, because what we will want to do, so we would like to attribute these values for each variable that we depend on, so that as to maximize p of x. But this problem may be modeled as a simple chain, because we have maximization over all the parameter x out of p of x. This is p of x max, which means that we have to maximize over x1, x2, and so on, xm, p of x. But is the same thing as before. If we define p of x in terms of the clicks, it means that only the first click depends on x1, so we can separate it. Only the second one depends on x2 multiplied with what's coming from here, and so on. Only the last one depends on xn. So we can do something like this. We can imbricate the maximizations, so such that only in the last maximization we have only one variable and only one term that depends on that variable, and this will return me something that depends on n minus 1. And then the next maximization depends only on xn minus 1 and results something that depends only on xn minus 2 and so on. After doing this, we get a term that depends only on x1. So once we obtain this term that depends only on x1, we can identify the value of x1 that maximizes that term. And then based on it, we can identify the value of x2 and so on, x3 and so on until we get back to xn. So the problem is similar to what we did for the sum product, but this time we're not doing summation, we're doing maximization. So if we, this is what happened in a chain, but we saw that sum product was defined on factor graphs. So if we want to generalize this to a tree structure, it means that max of P of X is maximization over Xn over all the neighbors of Xn over the terms that come to Xn and are received from factors. And what we need in order to compute this efficiently is to maximize as close to the leaves as possible. So the messages are sent from leaves to root, and the products, and the algorithm works recursively, identically as the sum product, but summation is replaced by maximization. And this is why instead of sum product is called max product. Now, another thing that is important is how we get to max product to max sum. Most of the time, for numerical reasons, when we do products of very small values, especially when we have long chains of probabilities, we get to values that cannot be represented anymore. We get to values very small or very large, and therefore the algorithm is not stable from numerical point of view. And to make it more stable, what we actually do is using logarithm, because we have this property that logarithm of a max is the max of a logarithm, and moreover, the logarithm of a product is transformed in summation. And this is why we get to from max product to max sum. And this algorithm works like this. If the message is sent from a node to a factor, we had 1 in the sum product algorithm. Now we have logarithm of 1, which is 0. And if the message is sent from a factor graph to a node from the graph, we have logarithm of f of x. Then we get to the recursion part. The message, if the message is sent from factor node to x, if you remember, we had summation over the product, the product between the factor node and the message is received by the factor node. Now, the summation is replaced by maximization, and now the product is replaced by summation. So we have, instead of the factor node, we have logarithm of factor node because we logarithm everything. Now, instead of product, we have summation over all the messages received by that factor node from the other links. We also have the allocation phi of x for each variable, so that to obtain this maximum value. So if we take max of this, we get to the maximum values. If we have R max of the same thing, we get the allocation phi of x, where we have something for x1, x2, and so on. So we have the states in which each such variable it should be placed. Okay. Now this is what happens if we have the message from the factor node to the variable node. If the message is from the variable node to the factor node, we, in the sum product algorithm, we simply had the product of all the messages received by the variable node. Now, since the product is replaced by summation, we will simply have the summation over all the other links of the messages received from the other variables. Sorry, so the message from variable to f is summation over the messages received by f from the other nodes. When we get to the root, we have p max as being maximization over all the terms out of of the root out of the messages received from the factor nodes to that root node. And also we can go, we can obtain the allocation for x, which is x that maximizes p of x, which will give us the value for s from maximizing this. Now we can go back. It's not backtracking as in the algorithm backtracking, but is getting back to see what is the allocation of all the variables that lead to this maximum probability, and this way we can identify the each allocation for each variable. So, for example, we have suppose that we have only 3 states for each variable. So this is xn minus 2, this is xn minus 1, this is xn plus 1, and so on, and before so on. So what's happening, based on the allocation from one step, we identify what is the allocation of the next variable that maximizes what we had until then. So we will have some chains like this that will flow in parallel until the last point where we have the 3 states, k equal to 1, 2, and 3. In here, we evaluate which of these chains lead us to the maximum probability. Let's suppose that we have this chain that comes from here and so on, and finally goes from here. And then we know that n plus 1 should be in state k equal to 3, n should be in state k equal to 3, n minus 1 should be in state k equal to 1, n minus 2 has to be in the state k equal to 2, and so on. In this way, we backtrack from the last variable xn to the first variable x1. Okay, and in this way we establish what are the what are the allocation, or what is the allocation of each variable from this chain of variables. Okay, so at the end, the last step, we are deciding what is the allocation, the right allocation for the last variable, and then we go back on the chain to see what were the allocation for all the other variables that lead to this maximization of probability. Do you have any questions? Okay, so to compute x max that maximizes p of x max, we pick an arbitrary node as root. It doesn't matter which root we choose. Compute and propagate messages forward from leaf nodes to the root, storing the received messages at every node. If the message is from a factor node to a variable node x, then we perform maximization over all the other variable nodes x1 to xm that are neighbors to the factor node, and the chosen values are saved for backtracking later. If the message is sent from a variable node to a factor node, then all we have to do is a summation over all the received messages. Now, when we get to the root, all we have to do is identify x max from the root, and then backtrack using the stored values to assign the states for each variable from this model. There are other algorithms that are similar to sum product and max sum algorithms. The junction tree, for example, is an exact inference on general graphs. works by turning the initial graph into a junction tree and then runs an algorithm that is similar to the sum product algorithm. If you want some details, you can find at page 416 in Bishop. However, this junction tree algorithm is intractable for graphs that have large clicks. Another option is to use loopable leaf propagation, which is some product on general graph. So we don't transform the graph, we leave it as it is. However, if it is cyclic, so if it has cycles, then we will not be able to apply a message like a message passing algorithm like some product. So therefore, in order to avoid this, all we have to do is to send initial unit messages across all links and leave the messages go around until convergence. So these messages will, it's like flooding the network and leave it exchange messages until the network stabilizes. But the problem is that this is not guaranteed um, to work. You don't know if the loopable leaf will lead to convergence. It is an approximate but tractable method for large graphs, but sometimes they work well, sometimes they don't work at all because, as I told you, it depends on the graph and if the message passing will converge or not. This is all that I had to tell you for today. Thank you very much for listening. Sorry again for taking so much time to finish. If you have any questions, I would try to answer. If not, then thank you again for listening to me. Hope you understood what I presented today. Have nice holidays and see you after the mini uh, holiday that you have. Have a nice evening and happy holidays. Bye
Thank
bye.
you. Goodbye.
Thank you. Happy holidays.
Thank
Bye bye.
you.
Thank you. Nice evening.